Rafael Ferraz, bienvenido. Déjame ver un instante. Junto con Renato Ferraz, no sé si es familiar tuyo, Augusto Rueda y Marcia Paiva, de la Espírito Santo Federal University de Vitória. ¿Vai falar portugués, español o inglés?
In English.
Ok. Adelante, tienes 20 minutos.
Okay. And Renato Ferraz is my brother. So, the title of this paper is An Integer Linear Programming Approach for Phasor Measurement Unit Placement. I am a co-author. My name is Rafael Ferraz, and the other authors are Renato Ferraz, Augusto Medina, and Marcia Paiva. This paper was developed in the Federal University of Espírito Santo, UFS, in Vitória, Brazil. The introduction. Nowadays, the constant change in the electric power system highlights the importance of studying tools to ensure the reliable and the secure operation of the network. In this context, it is essential to achieve the full observability of the system by measuring some variables such as nodal voltage and branch currents. A possible solution consists in the installation of phasor measurement units in a network. In this case, the phasor measurement units, they are the PMUs. This device, the PMU, is capable of measuring the voltage and current phasor in a power system by direct measurement when a PMU is located in the node or by using neighboring measured. The main gap of this paper is related to the prohibitive cost. So, the prohibitive cost of this device has encouraged studies which aim to minimize the overall cost of installing PMUs. And the proposal of this paper, in this paper, the optimal PMU placement problem was solved using ILP, the integer linear programming, in order to achieve the full observability of the system, minimizing the overall cost. The methodology. The ILP was compared with the genetic algorithm, the GA, the particle swarm optimization, the PSO, and Kuckle search, the CS, with the purpose of defining which one is the most suitable for this application. The networks used to evaluate the proposed methodology were the IEEE 13, 34, 37, and 123 node test feeders. These feeders were modeled as graph in order to introduce the domination concept of graph theory in this problem formulation and evaluate the optimization algorithm results use the upper and lower bounds of the domination number. So here we have some graph theory concepts. The first one, the graph G is denoted by a finite no-empty set of vertices V and a set of edges E. The minimum degree of a vertex of G is denoted by this delta, whereas the maximum degree is denoted by this other delta. A vertex V in a graph G dominates a vertex U if U is adjacent to V or U is equal to V. A set S of vertices in a graph G is a dominating set of G if every vertex of G is dominated by at least one vertex of S. And the minimum number of vertices in dominating set is denoted by the domination number, represented by gamma. So in here we have some equations. It is possible to define the upper and lower bounds of the domination number in terms of some characteristic of the graph. So in here, for example, the first equation, we have the variable n, that is the same of order, that is the number of vertices. The second equation, we have the variable m. M is the size, that is the number of edges. And the other equations that we have here present the variables n, m, and we have the deltas that are related to the degree. The PMU placement problem formulation. The objective function of the PMU placement problem consists in the minimization of the total system cost. This problem can be analyzed in terms of the minimization of the dominating set of the graph. So we have to minimize this function f, where n is the number of vertices of the graph, and xi is a binary variable which indicates the presence of a PMU at I. The constraint of this problem is represented by the observability requirement of the system. A complete observability means that all the system voltage, current, and frequency are known, either by direct measurement or by using neighboring measured phasors. So we have here the equation a plus 1 multiplied by x has to be greater than or equal to b, where a is the n by n adjacency matrix, I is the n by n identity matrix, x is the n by 1 matrix composed by a binary variable xi, and b is the n by 1 matrix of ones. The IEEE 13, 34, 37, and 123 no test filters were used to evaluate the proposed methodology. So here in figure 1, we have the IEEE 13 no test filter. In figure 2, we have the IEEE 34 no test filter. Figure 3, we have the IEEE 37 no test filter. And the last figure, figure 4, we have the IEEE 123 no test filter. For each one of this distribution system, a different adjustment of the metaheuristic algorithm was carried out. So here in table 1, we can see the parameters that we select for each optimization algorithm, in this case the GA, genetic algorithm, the PSO, and the Cuckoo search, the CS. And we select for each system, the 13, 34, 37, and 123. And it's important to note that these parameters were selected by tests. In order to compare the metaheuristic techniques, 10 simulations were performed. Considering some graph characteristics, it was possible to verify if the results of the optimization algorithm are between the domination number lower and upper bounds. So in table 2, we have some parameters of the graphs for each system. So we can see here the number of vertices, the number of edges, the minimum degree, and the maximum degree for each system, the 13, 34, 37, and 123. And with these parameters, we can apply in the 8th equation that I presented previously and calculate the lower and upper bound of gamma. So in here we have these bounds of each system. Now we have the results of the ILP, the metaheuristic algorithm, and the exhaustive search, the ES. And they are summarized in table 3. So here in table 3, we have the results of the objective function, the time of the simulation for each system, and the algorithm that we applied, the exhaustive search, the genetic algorithm, the PSO, the Cuckoo search, and the ILP. For the IEEE 13 no test filter, the 3 metaheuristic techniques and the ILP were capable of achieving the optimal solution. However, for the system dimension, the exhaustive search, the ES, is more suitable, considering the low computational effort required to perform this algorithm. In addition, the exhaustive search, the ES, is capable of providing all optimal solutions. The IEEE 34 no test filter, the GA, and CS achieved the optimal solution for all 10 simulations, whereas the PSO reached this solution 3 times. Compare the results of the ILP, the GA, and Cuckoo search. It is noted that the ILP presented the fastest convergence. The runtimes of the optimization algorithm were substantially lower when compared to the ES, the exhaustive search. The IEEE 37 no test filter, the ES was not performed due to the high amount of possibility to be tested. The CS was capable of finding optimal solution for all 10 simulations. The GA reached the solution 8 times, whereas the PSO resulted in the optimal solution 1 time. The ILP presented the fastest convergence. And finally, for the IEEE 123 no test filter, the ILP presented the best results based on the lower number of PMUs and the fast convergence. Additionally, the GA and the CS reached the optimal value 5 and 9 times respectively, whereas the PSO was not capable of reaching this solution from the 10 simulation performed. So the optimized solution achieved through the ILP regarding the PMU placement problem are shown in table 4. So as I told, the ILP got the best results. So here we have summarized for each system. So in here, for example, we have the system, the number of PMUs, and the PMU locations. So for example, for the system 13 node test feeder, the ILP selected 6 PMUs, and the locations, they are in the nodes 1, 2, 6, 8, 11, and 13. For the 34 node test feeder, the ILP selected 12 PMUs, and they are located in 2, 4, 7, 11, 13, 18, 21, 24, 25, 28, 31, and 34. And we have the results for the 37 and 123 node test feeders. The conclusions regarding the optimization's results, it can be concluded that the PSO is less suitable for this problem since this algorithm presents the highest average value of the objective function. On the other hand, the ILP ensured the globally optimal solution in addition to the fastest convergence when compared to the GA, PSO, and Google search. These conclusions highlight the importance of correctly choosing the optimization technique depending on the characteristics of the problem. It is possible to notice that the time required to perform the meteoristic techniques rises as the system dimension increases. Therefore, depending on the system dimension, this methodology may not be suitable. Furthermore, despite these meteoristic techniques can bring high-quality solutions, they cannot ensure that the solutions are globally optimal. And the last one, the ILP was capable of reaching the optimal solution for the analyzed distribution system with low computational effort. So thank you everyone for the attention.
Muito obrigado. Não temos perguntas. Se você quer alguma conclusão final, você é o último depois desta track.
No, that's okay.
Ok. Parabéns para você. Muito obrigado. Hein?
Obrigado.
Bom dia.
Bom dia.